Hello friends, Namaste, all of you, Namaste everyone, I am myself S.S.Takalkar. Of course, your friendly teacher. Dear friends, today we are going to study very important term in the thermodynamics, that is the enthalpy, and which is denoted by letter H. So, this term enthalpy, by the definition, it is the total heat contained of the system. So what is meant by total heat contained of the system? Consider. Suppose this is a system enclosing some gas, maybe ideal gas, having weightless and frictionless piston, and some opposing force is there, that is P external, P internal is also there, driving force is also there. Now, in such a situation, the system is said to be in a particular state, initial state, right? Then, if some heat is added, plus Q, heat is added in the system, what happened? Then, heat is added, that means minus of some heat, okay, plus Q, going here. Then this heat utilized to increase the internal energy. The molecules or atoms or whatever are in the system, they absorb the part of heat. Okay. And some part of the heat also utilized to done the work. And as this pressure is constant at equilibrium, then because of the absorption of the extra heat, the piston can be moved in this way, and there is a this original line. Some work is done increasing value, so work is done also, right? That is work, during the work. This is the displacement also, displacement done. Oh, so this work done. So in this way, when the heat is absorbed by the system, it is utilized to done the work as well as to increase the internal energy. And therefore, H can be defined as the internal energy plus pressure volume work. What is pressure volume work? That is the work because of compression or expansion of the gas against external pressures. So here the expansion process is shown, but not necessary. It may be a compression. Then depending upon the external pressure, it is more compression may be taking place. Okay. Now, so here the total heat contained, called as the enthalpy, can be defined as the sum of internal energy plus pressure and water. Okay. Now, if the initial state is going to change and the state is going to change, the other state can be obtained, and then one can write here, suppose the delta H is equal to delta U of plus. Now, the another state can be obtained, one can obtain P2 V2 minus P1 V2. What is this? That means how it is obtained. Suppose H is equal to U plus Pv, then H1 is equal to V1 plus P1 V1, and H2 is equal to V2 plus V2 V2. Then this H2 minus H1 is equal to V2 minus U1 and plus V2 V2 minus V1 V1. Okay. Right? So this is nothing but delta H is equal to delta U is equal plus V2 minus V1 V1. So I have write here directly. Now, in case suppose the equation can be applied for different processes. So if you consider isobaric process. What is isobaric process? that is constant value, sorry, constant pressure. So here delta H is equal to delta U. P1 and P2 are constant, say P. Okay. So what is obtained then? P delta V. Okay, P delta V. That is, what is that? That is P into P2 minus P1. Okay. Or if the isochoric process is considered, isochoric process. The isochoric process, that is at constant volume. The process carried out at keeping the constant volume in a closed vessel, closed water. The example of the isochoric system. Okay. Then what is obtained here? Delta H is equal to delta U. This is U. Then P is constant. V1 is equal to V2. Say V. Then it is V2 minus V. Or delta H is equal to delta U plus V. This is delta P. Similarly here, delta H is equal to delta U plus P delta. Okay. So this is the expression when the process carried out either at constant pressure or constant volume. Okay. Now one more thing, if the process carried out at isothermal. What is isothermal? Isothermal. Iso means similar, thermal means heat, temperature remains constant. Consider one more. Isothermal process carried out at constant temperature. So for isothermal process, what is it means? Constant temperature. That is delta T is equal to 0. And you know, internal energy depends upon the temperature. More is the temperature, more will be the internal energy. Or more will be the internal energy, there will be more temperature. That is delta U is equal to 0. Delta U. Delta U is equal to 0. So what is obtained here? Therefore, this one. Also, second. This is the one. Second. Also. At constant temperature, the volume of gas is inversely proportional to the pressure. That is Boyle's law. That is P is equal to constant. At T is equal to constant. So that is P1 is equal to P2 is equal to P3 is equal to constant. All this is constant. Or if you consider this one, okay. So P2 minus V2 minus P1 is equal to 0. Right? So here one can substitute here also. So ultimately the delta H is equal to delta U plus P2 V2 minus P1 What is obtained here? This is 0, this is 0. So here changing the enthalpy, total heat content of the system in isothermal process is found to be 0. Okay. So keep in mind this place. Now, if you consider a system consists of ideal gas. So what is the gas equation for this? PV is equal to nRT or P1 is equal to nRT. E at constant temperature. Then also P2 V2 is equal to N2 RT. Okay, constant. temperature remain constant, R is the gas constant, N1 and N2 are the number of moles, gaseous moles. Yes, only gaseous moles are considered. So P2 V2 minus P1 V1 minus P1 V1 is equal to N2 minus N1 RT. Or this is delta NRT. Right? Here P2 V2 minus P1 V1 is equal to this one delta NRT. But at constant pressure also. At constant pressure. What is option? N. And then what is here? P2 minus P1 is equal to this. P2 minus P1, that is P delta V. Therefore, what is option then? Therefore, as all these are the thermodynamic state functions. Therefore, delta H is equal to delta U plus delta M RT. What is delta M RT? Delta M RT. Delta N, that is the change in gaseous moles during the process. Whatever it may be a chemical reaction or any chemical change, chemical phenomena or any phenomena here. In the process, reaction is carried out at constant pressure at a given temperature. At given temperature. Specify given temperature. This is obtained where delta N is equal to change in gaseous mole. Change in gaseous moles. Gaseous only, not any other. Okay, is equal to sum of the products. Gaseous product. Gases. Minus sum of the gaseous reactants. Okay, this is the change. So here, second thing is now second. If we consider most change in enthalpy, already discussed here theoretically. If you consider any hypothetical reaction, say A plus B, B moles of B, give C moles of C, then D moles of B. Any hypothetical reaction such as A, B, C are not the reactions, not the products practically. Then the enthalpy change for this reaction can be given by the sum of the enthalpies of products. All the products. Sum of the enthalpies of the reactants. Products minus reactants. Considering their number of moles, number of coefficients in a given balance equation. So this can be product written as products C times the enthalpy of C plus B times enthalpy of B. Okay. Similarly, minus sum of the enthalpy of the A times and B times the enthalpy of excellent. Now, if exothermic reaction is there, some heat is liberated. Some given out. So whatever heat content of these and whatever heat content of this is less. Suppose there is 100 calories and suppose there is 90 calories and 10 calories go now. So 90 minus 100, that is negative value. So this is the exothermic reaction, right? Or exothermic reaction. What is delta H? Delta H is negative. And if however, consider this simple example. If the reaction is set in your endothermic, some heat is added. Suppose it has 100 calories heat, some 10 calories heat is added, then it is stored in this product. So it becomes 110. Product's enthalpy minus reactant enthalpy, 110 minus 100. It becomes positive value. Delta H is positive or endothermic reaction or endothermic process. If the delta H is negative for given reaction, so it is no doubt exothermic in nature. And if the delta is found to be it is positive, the reaction must be endothermic. It is absorbed, right? Now we are going to correlate this total heat content of the system, what is known as enthalpy. Remember always, very important thing about the enthalpy. The total heat content of the system cannot be determined. Its absolute value is not determined. Its change is determined. For example, if you consider for our understanding, I am going to write here. If you consider, can you measure the amount of water in a sea, or amount of water in any dam, or amount of water in any well, or amount of water in a given container? Very simple. Suppose this is a container, and there is the water. So it is complicated, but suppose this way. But if we add some heat energy, right? So the delta H becomes now H1, H2, right? Okay. Now it comes to here. Difference. So delta H is equal to H2 minus H1. Difference can be easily calculated. Okay, but to count all these total absolute value is not possible. Practically, therefore, the enthalpy of the system, when we are going to say the enthalpy of the process, that means it is the enthalpy change and not the H. It is always enthalpy change in the process. Oh, okay. Now we are going to relate the heat content of the system with heat capacities. What is meant by heat capacity? If you consider, one can consider, because it is very easy to consider. Imagine thing. If you consider iron, if you consider copper, if you consider sulfur. Okay. Now, if you supply the same amount of heat to the copper, same amount of the heat, same time, by same burner, to the iron, to the sulfur, okay. Amount is same amount, same. Okay. Then the initial temperature is supposed to be 1 degree Celsius. Whatever it be, 1 degree Celsius, 1 degree Celsius. And then after, when you heat the same time or same mass, then if you measure the temperature again using a thermometer, then it will be T2, it will be T2. Then delta T is equal to T2 minus T1 degree Celsius. Which one is more? In the case of copper, sulfur and iron. Okay. So it is found that it depends upon the nature of that substance. Okay. Copper absorbs heat very easily with high conductivity. Than sulfur. So it rises high temperature. Okay. Its temperature is more. Delta T is found to be more. Or second thing, if you consider these two materials, right? And we like suppose 1 gram of copper or 1 gram of we like to rise the temperature by 1 degree Celsius only, 1 degree Celsius. Which one require more heat? Copper or sulfur? Which one require more heat? Of course, which one? Copper requires less heat, less. Why? It is the nature. That depends upon the nature. That means it is, we are going to study the second problem, that is the heat capacity. Heat capacity of a substance denoted by capital letter C. So heat capacity can be defined as the amount of heat absorbed to raise the temperature by 1 degree Celsius dq upon dt. That is the heat capacity of that particular substance. So depending upon the nature of the substance, the heat capacities are. But this is general. So one can write here CdT is equal to dq. So here, if temperature increases, suppose 25 degrees Celsius to 26 degrees Celsius or 29 degrees Celsius or 40 degrees Celsius, etc. Then the particular amount of the heat is absorbed. So here one can integrate these terms both sides, taking integration dq. Okay. So the derivative and this the integration getting cancelled. One can write here T1 to T2. So here one can obtain here the T1 T2 is equal to here getting cancelled Q or C delta T. So delta T, that means one can write here T2 minus Q1 or C delta T is equal to, or one can write here C is equal to Q upon delta T. Okay. So here this can be written as delta T. Okay. Dear friends, now by the definition, it is not clear yet which substance has the higher heat capacity and lower heat capacity, unless you are going to take some similar substances. Therefore, the specific heat capacity or specific heat is considered. So, according by the definition, that is the amount of heat absorbed by 1 gram of that substance, right? So mass is 1 gram to raise the temperature by 1 degree Celsius. 1 degree Celsius, or it may be 1 degree. Whatever the difference is, not change the difference. Makes a difference. Okay. So the substance taken is 1 gram and temperature rise 1 degree Celsius. Whatever heat is absorbed, it is called as the specific heat of that substance. So amount of heat absorbed by 1 gram of substance to raise the temperature by 1 degree Celsius is called as specific heat. Okay, but in chemistry the rule is a very important rule, and therefore heat capacity generally considered as molar heat capacity. Heat capacities. If the process carried out at constant pressure, constant value. So this is called as a heat capacity at constant pressure, CPF. Molar heat capacity at molar heat capacity at constant pressure. Or molar heat capacity, right, at constant value, process carried out, molar, See here. So we are going to study what is they relate, how they relate. Okay. Dear friend, yet you know the specific heat of the substances depends upon that particular substance. It is the inherent property of that substance. Right? That means copper can easily heat. It has lower heat capacity. Whereas the sulfur requires more heat to raise the temperature by 1 degree Celsius per 1 gram specific heat capacity. Now, CPM, that is molar heat capacity at constant pressure. Okay, CPM. By the definition, E the heat is absorbed at the constant pressure Q. Heat absorption, amount of heat absorbed to raise the temperature by 1 degree Celsius for n moles. Number of moles. If N is equal to 1, N is equal to whatever other moles can be divided. So amount of heat absorbed by the substance, okay, at constant pressure to raise the temperature, whatever is the temperature, it may be increasing the temperature. Okay. Then further as you know, dQp is equal to, or one can say P is equal to dH or H by the first law of thermodynamics at constant pressure. At constant pressure, what is the first law? By first law, Q plus W. Q at constant pressure, W is what is W? Minus P delta at constant pressure. This is the equation. So here the delta U is equal to QP, and if you compare this equation first also, H is equal to U plus P, delta H is equal to delta U plus P delta V. Okay, so here this can be rearranged here like this, where QP is equal to this minus come to here delta U plus P delta V. Okay, this is from first law, and this is from the definition of the what you find here. Both are same. QP is equal to delta H. That is the amount of heat absorbed by the system at constant pressure is equal to change in the enthalpy change in the process delta H. Okay? Okay. All are state functions. H, U, P, P. All are state functions. Therefore, one can write here delta H is equal to delta U plus P delta V at constant pressure. See? At constant pressure. And if you consider the first law of thermodynamics, if heat is absorbed at constant pressure here, as the work done is at constant pressure P delta V, when it changes, pressure remains constant, then on rearrangement we can obtain from the first law that QP is equal to delta U. QP means amount of heat energy that is absorbed at constant pressure, or the total heat content of the system are not different at constant pressure if the process carried out. Is it okay? Then now consider this. Okay. Then one can write here this is equal to then dQ. Okay. ds small enthalpy change delta T. This is maybe written as small letter T, absolute temperature, absolute degree Kelvin as K is used delta T. Okay, and R simply by for measurable change for a single step infinitesimal change is considered delta T n. N may be a number of modes, n may be 1, 2, or theoretically. Then, if the change in the temperature is small, so this can also be written as dT also. Okay. Or, in short, what is delta S and delta H is equal to Cpm molar heat capacity n times. Okay, and is delta T. Similarly, if the process carried out at constant volume, then the heat capacity at constant value, molar heat capacity at constant value is equal to dQB upon delta T n, or du upon internal energy change when small amount of the temperature increases per mole, or this can be delta U upon delta T per mole. Okay. Or that is delta U is equal to the molar heat capacity at constant value n times number of moles are there. Okay. And delta T. Here, these are very important. We are deriving, comparing the different concepts, and we are going to solve some problems during the proper times. Dear friends, as for the heat capacity, molar heat capacity, and the at constant pressure and constant value, these are the final expressions. Now we are going to compare the molar heat capacities and the enthalpy change, the internal energy change with the R, capital R, that is the very famous constant, ideal gas constant. Okay, how? Consider now. Consider. We are going to derive the relation between the relation between Cp and Cvm. Molar heat capacity at constant pressure, molar heat capacity at constant value, and gas constant R, capital R. Yeah. Consider relation. Consider H is equal to U plus P. Okay. Now, as ideal gas, the process between the molecules are set to be 0. Now, when ideal gas in a system if Pb is equal to nRT. Okay. So we can represent this terms also dP upon dT plus V times plus this P times dP upon dT is equal to number of moles, it is constant, R is also constant, dT upon dT. Okay. So we can this is getting cancelled, and at constant pressure dP is equal to 0. Therefore, this dP upon dT is equal to also 0. Therefore, 0 plus dP upon dT is equal to nR. Okay. Yeah. Okay. Right here. So this PdV dt, okay, is equal to nR. If n is equal to 1, PdV dt is equal to R. This is equation 2. From equation 1 and 2, one can simply right here. Okay, compare these two. What is happening here? dH upon dt is equal to du upon dt plus R. What is dH upon dt? dH upon dt. Course, the process carried out at constant pressure, the enthalpy change per unit change in the temperature, it is Cpm. And at constant pressure, the du upon dt, we have discussed, this is nothing but Cvm. Molar heat capacity at constant value, du upon u. Right? And dH upon dt plus. Okay? So, consider the technologies first. Now, as the enthalpy, what is by the concept, it is the total heat content of the system at constant pressure. Generally, why at constant pressure? Because almost most of the processes are carried out at constant pressure, but not necessarily the pressure is always constant. Therefore, the total heat content H here can be defined as the internal energy of the system plus pressure to pressure. What? So, it may be ideal gas or real gas. The equation can be applied here. We are going to study the Kirchhoff's equation. Or reaction or chemical reaction which can take place at two temperatures. Consider a hypothetical equation or hypothetical reaction. A giving some B product. So reactor reacts particle products. And if H1 and H2 are the enthalpy changes of reactant and the products. Okay, when some process taking place, right? But if the temperature changes, different temperature, it is not a thermal process. If the temperature changes from T1 to T2, temperature changes from T1 to T2. Then what happens? As the temperature changes, the heat absorbed or heat content of the system going to change. Therefore, one can differentiate these terms like this. First, consider enthalpy change that is delta H or heat of reaction, as well as heat of reaction. Okay, heat of reaction. Delta. Second, given by, of course, the total enthalpy of the product, right, H minus enthalpy of the H2 minus H1. Now, the temperature changes from T1 to T2. Okay, temperature changes. Then differentiate the equation with respect to temperature. Okay, so here the dt of delta H is equal to d dt, right, dt of H2 minus dH2 dt minus dH1. So what is it? So this is nothing but dH2 dt, that is a molar heat capacity of the product, right? Minus, yeah, molar heat capacity of the reactor. Molar heat capacity of the product minus molar heat capacity of the reactant. That is obtained delta C F. Okay. Rearrange becomes delta CPM dt to the numerator. Now this is for single step. One can take integration to both sides. Take integration to both sides. Right. If we have to select the limits, proper limits, initial limits, because temperature is going to change. So at temperature T1, the delta H of the reaction, heat of reaction, enthalpy change of the reaction is said to be H2. And if at T2, the heat of reaction, okay, right here, enthalpy change is delta H1 and it is equal to delta H2. Then take an integration in a proper limits, like here. It is okay. Now consider this equation. H is equal to delta CPM. This is the variable temperature changes T1 to T2. At temperature T1, the heat of reaction is said to be delta H1. At temperature T2, it is the H2. So one can write here delta H, L2 integration will be cancelled, and one can upper limit minus lower limit delta CPM. This is the integration with respect to temperature is said to be a T only, simple T, and this is T2 and T1. So here subtraction delta H2 minus delta H2 minus H1 lower limit and upper limit minus this lower limit. Substitute here delta H1. Okay. Upper limit minus lower limit. These are the values of the heat of the reaction at given temperature T1 and T2. Delta CPM. This is the, of course, the T2 minus T1 as 1 CPM. So here delta H2 is equal to, one can rearrange the star delta H1. Okay, here plus delta CPM T2 minus 1. So this is the Kirchhoff's equation. And what is the application? E, consider. If you know the molar heat capacity is constant pressure at any temperature, suppose T1 and H1 are known, then H2 can be determined. Or if CPM is known, T2 is known, then for any other temperature T1, delta H1 can be determined. So certain reactions, it is not possible to carry out practically, not possible to carry out any temperature, very low temperature, very high temperature. Then on the using this equation, the delta S, that is heat of reaction, can be carried out. Suppose delta S2 can be carried out for any other unknown temperature, practically not possible. At this temperature, delta S2 can be calculated if delta H1 at this temperature is known for a given substance, given system. In this way, similarly, one can write here as similarly the delta, instead of total heat content at constant pressure is considered, the internal energy change can be written for this, and plus the molar heat capacity at constant value is considered. Okay, dear friends, we are going to stop today, and during the next lecture I bring a very interesting topic for you. Thank you.